Why are chips harder to manufacture than atoms? The first step in silicon wafer manufacturing is refining high-purity silicon using quartz sand. You can also crush shearing rock and put it in the generator. Heating at high temperature extracts polycrystalline silicon, which is then put into a crystal seed. Using the Joukowsky method, it can be pulled from silicon melt to form a single crystal silicon ingot suitable for wafers. Then cut it into wafers. Each wafer usually has a diameter of 300 micrometers and a thickness of 0.75 micrometers, costing approximately $100. It can produce 230 CTU chips. Each chip is approximately $552, equivalent to a crystal ball worth approximately $126,960. These crystal balls are very fragile and can easily shatter, so they need to be sealed and transported in a suspension box. The overhead track prevents collisions during the encapsulation process and saves more surface space. The sealed cassettes transport the wafers to different equipment, each with a specialized mechanical arm. It can safely take the wafer out of the sealed warehouse and place it on the equipment for processing. Now the crystal boule will go through the second round in the photolithography machine. Second step, applying a photoresist layer, then using a baking tray to heat the wafer to accelerate the evaporation of the photoresist and immediately sealing it to transport the wafer to the lithography machine for the third step. Photolithography utilizes ultraviolet rays to project through pre-designed templates, enabling light to pass through and etch detailed nanometer-scale patterns on photoresist-covered crystals. The photolithography machine is one of the most important tools for making chips. Its interior is composed of three key parts: an ultraviolet light source, a focusing lens, and an optical film. The optical module includes pre-designed template patterns, usually configured based on the size of the chip to be made. Typically, an optical mask can hold 2 reticles, and a single chip requires at least 80 different optical masks. Each photo mask costs over $300,000. When the light engraving machine starts, ultraviolet light passes through the photo mask and enters the lens of the focal line. After multiple refractions, the image on the retina will shrink 4 times and be projected onto the wafer, imprinting it until the first layer of 230 chips is complete, at which point it will stop. Then apply the developer to wash away the weak areas. Leave the remaining images clearer. Bake it again on the hot plate to harden. After the first layer of the membrane is constructed, move to the third step where ion implantation equipment treats the silica outside the membrane. Continue until the previous layer metal wires appear and peel off the photoresist on the wafer. Next, proceed to step 4. Spray tan bronze and other metallic materials onto the wafer to fill and cover spaces. Next, a polishing machine is used to flatten the accumulated metal material on the crystal surface. Expose the first layer of silica and copper to proceed with step 5, ion implantation. Before this, the wafer still needs to go through the first 2 steps. By printing the photomask, we can start doping with elements like boron and phosphorus to alter the electrical properties of the material, giving the chip different conductivities and hardness. This allows for the production of various types of chips. The first layer of the chip has been etched. Now on to etching the second layer. The wafer needs to be transported to cleaning equipment first, where ultra-pure water will wash away the dust particles. Then it is dried using either nitrogen gas or a hot air oven, and sent it to the inspection equipment to check for any defects in the crystal tubes and metal layer using an electron microscope. Then we can start printing the second layer. Typically, a chip consists of about 80 different layers. Each layer has to go through at least 5 steps, taking a minimum of 3 months to complete 940 processes. This is a CPU chip. We'll enlarge it to see the different regions inside. We choose an area to continue magnifying and can see the crystal structure arrangement on each layer of the chip. These crystal tubes are smaller than grain particles. Even a speck of dust is millions of times bigger. After comparing it to a single hair, you will realize just how tiny those microchannels are. In a chip, 80 layers of different circuits need to be imprinted. Typically, an intelligent machine contains 62 V-chips. The combined size of these chips is almost like an ant. This shows how difficult it is to make chips because the transistors on the chips are so small that they are easily affected by dust. For example, using Intel CPUs, from i9 to i3, different efficiency grades are categorized. As the internal crystal structures degrade, their value decreases. There are only a handful of countries in the world capable of producing such high-end chips.